Well, thank you very much. Good morning, everybody. Today I'm going to talk to you about a very simple solution to what seems to be a very complicated problem. The problem is how to guarantee latency in data center networks. And the solution we call queue-jump, which is described in our paper, Queues Don't Matter When You Can Jump Them. So we've all heard about these data center networks. They have lots of wonderful properties. We can assume that they have more or less commodity hardware components, and that the networks are built out of static topologies that don't change very much or very frequently. We can also assume that they have kind of a single administrative domain, or a set of administrators who are looking after these networks and making sure that they are running and that policies can be applied to all of them. We can also assume that there's some sort of level of cooperation in these networks, that the machines are there to serve a kind of a common purpose, at least up to the hypervisor, but sometimes also beyond. And we can assume that they are statistically multiplexed. That is, they're built using the same kind of fundamental technologies that we use to build the internet. Now, one of the downsides of the statistical multiplexing is that it offers no latency guarantees. And that's because packets in these networks are served on a kind of first come, first served basis. And so you can't really tell how long it will take for any one packet to cross the network. So you may wonder, well, does this really matter? Does this have any kind of impact? And so to demonstrate that it does, I'm just going to walk through a little example that we set up on our local cluster. So we set up a 12-node cluster, all running 10 gigabit commodity Ethernet. And on 8 of those machines, we installed the Hadoop MapReduce system. On 2 machines, we installed the PTP time synchronization system. And on 2 machines, we installed the memcached key value store system. Now I'm going to use this as a kind of a running example as we work through this talk. So this graph is a bit of a running one. You'll see that what we've done is run a kind of a 10-minute long experiment, and I've just selected out a 200-second segment of that experiment. So this is 150 to 350 seconds on this experiment. And on the y-axis, what I've got here is the synchronization offset. So that's the difference in the time that's sensed between the client and the server of PTP. And you can see that this is around about 0 here. In practice, it's about 5 microseconds of offset. Now I'm going to put on the same axis the memcached results. In this case, what we're looking at is actually the latency of requests that the memcached client is seeing when it's sending requests to the memcached server. And you can see it's not quite as regular. It's a little bit more bumpy. And the reason for that is that we've got a mixed get-set workload of about 90 to 10 split. But you can see it's pretty regular there, around about 400 microseconds worth of latency. Now, in these 2 cases, we were running these systems completely alone on the network with no kind of interaction or interference between them. They were just running on their hosts and nothing else was running at the same time. If we sort of turn all of these things on together when we run them at the same time alongside Hadoop, then we end up with a very different kind of scenario. What we see here is that Hadoop starts to interfere with the performance of memcached and of PTP. And you can see these big latency spikes happening. Every time Hadoop does a shuffle, it hits the network pretty hard, and this causes a lot of queuing in the network, and this delays the traffic that we're seeing from memcached and from PTP. And so for many of you who've come here from a long way, you'll have a very visceral sense of what the problem is. The problem is, of course, queuing. So if we were to sort of crack open our switches and have a look inside and see what was inside them, we'd probably see something that looks a little bit like this. So we have here a switch, and we've got 4 hosts that are all sending to one of our hosts. And this could be anything. It could be one of our PTP or memcached clients. And you can see here at the front of the queue is a whole pile of Hadoop packets, lots of heavy traffic, which is causing this big backlog of packets. And behind them, in the sort of mix of packets there, are the memcached and PTP packets. And they're being delayed in the progression through the switch. And this is what's causing these sort of latency variations that you're seeing. So in general, we're going to define a term which we call network interference. And that is that when congestion from one application, such as Hadoop, causes queuing, it delays traffic from other applications, such as memcached or PTP. And in order to solve this, we're going to step back a little bit in time, and we're going to take some of these ideas from the QoS world, some very, very established research. We're going to build on that. But what we're going to do is we're going to modify it for the data center context. We're going to take these ideas and apply simplifications and new assumptions that are true in the data center that aren't necessarily true in the wider internet. And so just to revisit those very quickly, we're going to assume that we have a relatively static network that doesn't change very much or very often, that we have a single administrator who can apply these policies to the network wide, and that we have some level of cooperation between all of these hosts. So these hosts are working together up to at least some point. But we also don't want to stop there. We want to make sure that our system is kind of deployable tomorrow. We don't want it to be just another long-term research project. So we're going to add some extra constraints. And those constraints are to make sure that we can run with unmodified binary applications. So applications stay exactly as they were when we first got them. We also want to make sure that we don't have to modify the kernel code in any substantial way. We don't want to apply patches to kernels and to have to keep bringing those patches up to date every time the kernel version changes. We don't mind running against a kind of standard binary interface, ones that don't change very frequently, but we don't want to have to keep source code modifications up to date. And we also want to maintain this really fantastic property that we have with these data center networks of running commodity hardware. So working within those constraints is where we're going to try to find our solution to this problem. So to dig into that a little bit, what I want to look at is kind of two different types of delays that are going to happen as a result of these queuing. So the first is just sort of classical queuing delay. And this is where we have a packet that is latency sensitive, such as the one there, number 7 in green, which is delayed and stuck behind a whole pile of other packets, and it's waiting to finally get to the front of the queue. The other type of delay I want to talk about is what I'm going to call servicing delay or scheduling delay. And that's where once a packet has already made it to the front of the queue, it's just waiting for the switch fabric to finally get around to putting it across. And you can imagine that if it took some time for that to happen, for the packet to cross the switch fabric, then new packets could start to build up and add up behind them. And as this process happens, we end up with more and more queuing. And as a result, you can see fairly intuitively that servicing delay ultimately is what causes queuing delay. And so there's a fairly simple intuition of what we're going to do to address this. What we're going to say is if we can find some sort of way to pace or space out the packets that are arriving at the switch, and if that would be equal to the servicing delay, then we won't actually experience any queuing delay. And that's the kind of basic principle that we're going to apply behind this queue jump and its ability to provide latency guarantees. So in general, what we're going to say is if we can find a bound for the servicing delay, and we can rate limit all of our hosts so that they never experience queuing delay. And that's the kind of basic idea that QJump uses. So just to walk through how we find that bound, we're going to apply some very pessimistic assumptions. We're going to assume in this case, on this diagram, that I have 5 hosts in my little network here, and that 4 of those hosts are all sending to the one output host at the same time. So in this case, we've got 4 hosts, and we've got an edge speed of our network of, say, 10 gigabits per second. We're also going to assume that there's an upper bound on the size of packet that we can transfer. So for this example, I'm going to say P is 1,500 bytes. And on the basis of this, it's fairly easy to calculate the serialization delay, which is how long, in the worst case, a packet will take to cross the switch. And so that's just the rate divided by the packet size divided by the rate. And since we have 4 queues here, we can simply multiply that by the number of queues, and that gives us a fairly pessimistic bound for how long it's going to take for the switch to service all of those packets. So in general, we're going to call the servicing delay this fairly simple equation where we have n the number of hosts, p the number of bytes sent, and r the edge speed. And this is true so long as the switch implements a more or less fair scheduler, which has been true in any of our experiments. It turns out you can actually generalize this equation to a whole network. I'm not going to go into the details in this talk, but you can find more details in the paper. So the idea here is if we apply this rate limiting, we can end up in a situation where we minimize the amount of queuing delay. And we're going to do that by defining what we call a network epoch. So we start with what we call with a idle network, so there are no packets in the network of any sort. We allow all of our hosts to send at most p bytes into the network. And then we wait one of these delays for the packets to get through. And once the network is again idle and all the packets have finally filtered through, we can then go back to 1 and we can start all over again. So that's the basic idea that we're going to apply, but there are, of course, 2 problems to this idea. Now, the first problem is synchronization. So far, what we've been doing is assuming that all hosts are sending exactly the same time. And so what I've got here is illustrated as 2 of these network epochs with all the packets nicely aligned and all of them being sent at the same time. And you can see here we have 4 packets in the first epoch, 4 packets in the second epoch, everything's looking great. But in order to do this, we'd have to have a lot of synchronization, very tight synchronization between all of our hosts, and we don't want to do that. So what I'm going to do is sort of break this up and allow the synchronization to slide. So we call this this is a mesochronous network. And in this case, if the synchronization slides, you can end up in some kind of pesimal cases. And you can see here what we've got is twice the number of packets essentially with respect to one epoch. So it's actually quite easy to handle this. We simply add a factor of 2 into our epoch equation, and that handles this mesochronous case and allows us to remain the system unsynchronized. Now there is, of course, another problem, and I'm sure you're all thinking it already. It is the dark side of our epoch. And the problem here is throughput. We have this rate, and we're dividing it by the number of hosts, in fact, double the number of hosts, and this results in a very pesimal-looking rate limit. And with our little simplistic example of 4 hosts, it probably doesn't look so bad, but if we were to use a high-speed network and a lot of hosts, then we end up with a very pesimal-looking rate limit here. Now, you should keep in mind that this very small 5 megabits is actually quite a strong 5 megabits. It's one at guaranteed latency, so we know that all packets in the network will get through within a bound, but it is still quite a low rate. So there are lots of applications that can actually handle this fine. There's plenty that, so for instance, PTP doesn't really send more than a few packets a second, and that would be quite fine with a 5 megabit rate limit. But of course, there are plenty of applications that can't handle this, and so we want to come up with some sort of way to handle these new situations. And the way we're going to do that is we're going to just stick our heads in the sand and assume that there is no problem. So the solution here is to kind of assume the problem away. And by that, what I mean is, at the moment, we've started with this very pessimal assumption of all hosts sending to one host on the network. So we've got this oversubscription ratio here of 4 to 1. But you can imagine if we had 1,000 hosts on our network, 1,000 hosts fanning into one host is a bit of a silly scenario. So what if we just assumed it away? What if we just assumed that half of our hosts were sending? Well, that gives us a wonderful property, and that is we can double the amount of traffic we can send. And you can imagine taking this a step further. What if we assumed that only a quarter of our hosts were sending? In that case, we can send at 4 times the rate. And so we can get lots of rate benefits with the same kind of delay. Now, of course, if our assumption is wrong and we end up with more packets in the network than we expected, well, then we're going to end up with queuing that we don't want, and we're going to end up with latency variation that we don't want. So the obvious question is, well, what is the right assumption? What should we make as our correct assumption? We can assume a 4 to 1 oversubscription ratio, and this gives us a very low throughput rate limit. But it also gives us a very tight-looking latency distribution. So all of our latency falls within our bounds, and we end up with this much nicer distribution. On the other hand, we could, of course, assume a 1-to-1 subscription ratio, and in that case, we get line rate throughput, and that's a fantastic thing for throughput-intensive applications. But we end up with a skewed latency distribution with very long tails. And in fact, there's a whole collection of these different assumptions we could make, and they don't even have to be integer values. They could be anywhere in the spectrum. So what we're going to do is we're going to pick a couple of these assumptions, and we're going to layer them together using hardware-enforced priorities in the network. So to work through an example, if we have our low latency traffic that's very latency sensitive, we can give it the highest network priority, and that will ensure that it's always at the front of the network queue. If we have medium latency sensitive traffic, so for instance a memcached, which is somewhere in between the latency sensitive and throughput intensive range, we can give it a medium priority. And so it puts it somewhere in the middle of the queue, ready to snap up any opportunities of missing packets whenever it can. And finally, for our very throughput intensive applications, for instance Hadoop, we give it almost no rate limit at all, and we give it the lowest priority. So wherever there is space in the network, it'll be able to fill its packets in, but it won't be interfering too much with our latency sensitive packets. So you can see that what we've done here is actually produce a very nice looking network schedule. And actually in our paper what we do is we compare this network schedule to a near optimal schedule, the pFabric system in simulation. And there's more details in the paper about how that looks and works. So what we've got here is the ability for our low latency packets to jump over these queues. And the fantastic property of that is that these queues now no longer matter because these packets can jump them. So the general idea here is that we're going to use hardware priorities to run different queue jump levels, that is, these latency versus trade-off levels. And they're going to run together using these priorities, but they'll be isolated from each other. At least the latency effects will be isolated from the priorities below them. So the key to making this work is to implement an efficient rate limiter, and we've done that with a bit of code that we wrote ourselves. The code is more or less what's on screen. Don't worry about reading it too much, but that is a fairly accurate sample of what we actually ended up writing. We use the Linux TC, or traffic control interface, to implement this, and our code runs at about 36 cycles or so per packet, so we're pretty efficient in terms of cost on the CPU. We also did a little bit of smart buffering, which we describe in the paper, and this is to get rid of some very nasty effects that TCP has when it sees large amounts of packet loss in the host. And we used the LD preload library in order to intercept applications as they were making socket calls, and this allows us to apply these priorities to unmodified binaries. And finally, we just used standard Ethernet VLANs as our mechanism for enforcing priorities, which is available on just about any commodity switch. So if we come back to this running example, here we have our situation where Hadoop's traffic is causing queuing in the network that is interfering with the traffic from Memcached and from PTP and causing these latency spikes. If we now appropriately rate limit and prioritize the traffic from PTP and Memcached, we end up in a situation that looks like this. And that is, as you can see, almost identical to the base idle case. And so the performance here ends up being very good. Now, of course, this is a small scenario here, and we wanted to compare against lots of other systems. And so we're going to compare against some other systems that are, in our same sense of the word, deployable. That is, they don't involve any of these changes that we consider to be limiting for deployment. So this graph is a little bit of a complicated one, and you don't need to worry about too much what the access means. What we're showing here is the normalized root mean squared application-specific metric. In this case, the application-specific metric for Hadoop is the Hadoop runtime. That's the time it takes for any one job to run. For PTP, it's the synchronization offset. So that's the delta between the time in both systems. And for Memcached, it's the request latency. And what we've done is normalized these values to an ideal network. That is, an idle network where there is no traffic of any sort. And so in the first column, which is different to all the other columns, these applications are running entirely by themselves on the network. If we run them all together and they're all running on the same network at the same time, we get this very different picture. And in this case, Hadoop's runtime isn't affected very much at all, but PTP finds itself about 300 times worse than if it was in an idle case. And Memcached is about 1.5 times. Now, the most obvious solution to apply in this case is to apply something that will control queuing, and most switches implement Ethernet flow control extensions, so that's a very obvious thing to try. It turns out the Ethernet flow control extensions really are working to minimize loss in the network, and they do this by making their queues quite long. And you can see here that PTP ends up being about 12,000 times worse, so it's not actually doing very much for this particular problem. Another kind of queuing control that's very widely deployed and available is ECN, or explicit congestion notifications, and our switches implemented the WRED functionality. Now, there is a problem with ECN in that you have to try and calculate or figure out what the correct upper and lower thresholds are for configuring it. So what we did was we incremented, or rather iterated, over a large space of these configurations, and we picked the best one that we could find. It turns out that it wasn't actually an optimal solution for any of these systems, but this one was the best that we could find. So here, Hadoop's runtime is being affected fairly severely. It's about 2.5 times slower than the ideal case. And Memcached and PTP are running at more or less ideal. They're a little bit under there, and that's just within the measurement noise, so more or less 1. So this did pretty well, but it was quite severely affecting Hadoop. The other thing that we could try is to use DCTCP, which is a sort of new kid on the block here. And you can see that DCTCP has done quite a good job. It's actually the best solution that we've tried so far. In this case, everything is brought into a reasonable range. PTP is about 2.5 times worse, but it's doing quite well. Now, currently there's a problem with DCTCP in that the way it's deployed is as a kernel patch. And we had to do some work with this kernel patch to move it forwards from the 2.6 kernel that it was deployed with to our 3.4 kernels. This was a bit of work, but it's not insurmountable. And we expect that in the future, DCTCP will be deployed as a kernel extension and not have to do this work. Finally, putting QJump onto the diagram here, we can see that QJump actually does the best out of all of these systems, performing at very close to 1, which is almost ideal. So in conclusion, you can see here that QJump applies these sort of data center simplifications to the QoS rate calculations. And this allows us to get a nice set of service levels ranging from guaranteed latency at very low throughput all the way through to line rate at variable latency. And finally, we've shown that it can be done. We can deploy this without any modifications to applications, to the kernel binary or source code, and also to the hardware. So obviously, this is a very short introduction to a much more detailed paper. And if you want to find any more details, there are many in the paper. We discuss ideas about what happens when you share ingress and egress ports on the machines. We discuss a whole collection of other applications and what their effects are, as well as switches in more detail. We look at how to calculate these rate limit calculations and what the correct trade-offs are between these calculations. We also look at what the right bucketing is for these different queue-jump levels and what happens if you get them wrong. We built some applications on top of queue-jump, so we built a very high-performance two-phase commit system that makes use of queue-jump's guaranteed latency to introduce very short timeouts and very high performance, even in the presence of very extreme network pressure. And finally, we ran queue-jump as a network simulator in comparison to pFabric and DC-TCP, finding that it outperforms pFabric in many cases, especially for tail latencies and very small flows. So while I'm on the topic of the paper figures, one of the cool things that we've done with our paper is to, if you see the figures in the paper, you can in fact click on the links for any of the papers, for any of the figures. When all of these figures actually link through to our website. And on our website, what you'll find is detailed descriptions of every one of the experiments behind every one of the figures. So this includes all of our source code, all of the patches that we made, all of the tools that we wrote for collecting and analyzing the data, all of the raw data that we collected, and everything including the plotting scripts we used to generate these figures. So you can, in fact, reproduce any one of the figures given our source code and data on the website. And all of the figures you can find in the paper are linked through onto the website, and you can get to that separately as well. So on the website, there's also a ton more details, as well as links to other similar publications that we've done in this space. So with that, I'm happy to conclude, and I'd be happy to take any questions. Thank you very much.
So the mics are on both sides.
I'm Vedat from Google. Really great presentation and paper. I'll start with two observations. First, great job in making all your results available on your website. I did have a chance to look at that, and it's really well done. I think a great example. Second, best use of 106 slides in a 20-minute presentation I've ever seen. So great job with that. But now my question. If I were to compare your results with a naive approach of taking 3 QoS classes for latency, low, medium, and high, how would that have compared to the results that you delivered? In other words, I just put one in high, one in medium, and one in low, and ran like that.
Sure. Oh, so your first problem is going to be what rate limit do you set? And that's
no rate limit.
Oh, so you just mean priorities alone? Yeah. So this will work fine as long as you don't have too much fan-in. So if you don't experience too much in-cast scenarios, then you'll probably be okay. But one of the reasons behind the rate limiting is to give you these guarantees, which will be violated if you have too much in the way of in-cast. So yeah.
Do you have a sense for what things will look like for your experimental setup?
Sorry?
Do you have a sense for what things would look like in your experimental scenario, given whatever level of
in this particular setup, I think that it'll look pretty much the same, yeah. This is sort of an optimization for much bigger setups, yeah.
Go ahead.
Okay, hello. I'm Wei Bai from the Hong Kong University of Science and Technology, and thanks for your nice talk. I want to know, have you considered using weighted fair queuing to handle the network interference? Because compared with your solution, there's no starvation issue for the weighted fair queue. And weighted fair queuing is also work conserving.
Sure, yes. So actually what we've done is general unweighted fair queuing. And what you can see is if in the appendix to the paper, you can have a look at our derivations where we start from a weighted fair queuing model and work our way to our final result. We haven't considered using it because of our constraints to use commodity switches. So you could do that. We don't actually experience starvation because of our factor of 2 that we add into the system. So that actually isn't a problem for us, but there are ways to derive from a weighted fair queuing model to what we have.
Thanks.
Hi there. I'm Luis Pedrosa from the University of Southern California. Congratulations on the Best Paper Award. It's absolutely amazing. I'd like to change the assumptions that you use in this presentation just a little bit. And I'm sure that you've thought about this before. So a lot of workloads in modern data centers do not assume that you can control the client completely. It might be running a VM that is controlled by some other client. And as it is right now, you sort of have the clients voluntarily pacing themselves. Now, I could imagine you could easily put this at a hypervisor level, maybe relax that assumption that you cannot control the kernel. I'm wondering if there's any hidden challenges there when you don't have full cooperation from...
Sure. So we actually don't assume full cooperation from applications. Our module is implemented as a kernel module, and so applications are actually unaware of what's happening to them. There's no reason in principle why you couldn't take our kernel module, implement it in the hypervisor. It just turned out to be easier to build it in the kernel. There is in principle, problem which is deciding on what the right rate limit for a given machine is, and then a subset of those rate limits for applications. So that would be a potential stumbling block, although I think it's just an application of the same calculations. You just got to be slightly more careful about how you pick the values. But in principle, I don't see any reason why you couldn't do that yet.
Thank you very much.
Sorry, I think we can take one more question. Could you?
Bill from Tsinghua University. So I noted that in your assumption for the synchronization scheduling, you suppose each packet has a fixed size that of 1500 byte. Actually, every packet has different size. So,
Yes,
yeah,
absolutely.
That's my question.
We don't actually assume the 1500 byte. What we assume is that there is a limit. And in actual fact, we assume that there is a maximum number of bytes that can be injected into the network in any one epoch. So in our example, we use 1500 bytes, but in practice, what we care about is the maximum number of bytes that are issued into the network for a given epoch. And in order to give a latency guarantee, you'll have to pick a number for that, and that's just an unfortunate consequence of the maths.
Please make it a quick one.
Hi, Jonathan Perry, MIT. So the problem with kind of these rate limiters or queuing disciplines in the kernel is that you're moving a lot of the queuing from the network to these to the kernel, to the endpoints. Does this kind of that movement of queuing to the endpoints, does that change the end-to-end latency that you observe?
Very good question. Yes and no. So you may recall when I introduced the implementation that we said we do some smart buffering. This is an attempt to mitigate that effect. So what we do is we resize the buffers that send buffers and receive buffers that applications are given, so that when they push too much traffic beyond their rate limit into the network, they receive pushback directly from the kernel. So in this case, they'll receive an no-buff error. So there are, in fact, two ways you can do this. You can give them their regular size buffers and they can experience delay, or they can experience pushback directly. And this is sort of an application-specific question. If you care about latency once in the network, you can allow the buffers to queue. If you care about end-to-end latency, then you're going to have to experience that pushback straight away and never exceed your rate limit. There is a slight modification, which is in our kernel code, we allow applications to be automatically demoted from their high priority, low throughput to a lower priority at higher throughput. And this kind of allows automatic configuration. That code isn't very well discussed because it's got a couple of quirks in it, but the released code has that feature and you can try it out here. Thank you very much.
Let's thank the speaker.